All right, welcome to the Explainer. Today we're going to tackle a massive question that actually has a surprisingly simple answer. How in the world do you measure something you can't even touch? You ever look at a mountain and just wonder, how do we know how tall that is? Or what about the distance to the moon? I mean, it's not like somebody ran a giant tape measure up there, right? The solution is all thanks to a really powerful idea called indirect measurement. So, can you measure a mountain with just a regular old ruler? I mean, that sounds nuts, doesn't it? But the secret isn't about getting a longer ruler. It's about using a really clever idea from geometry that lets us figure out huge distances, all from right where we're standing. Okay, so the big clue here, the secret sauce, is a concept called similarity. And trust me, once you get this, you're going to start seeing it absolutely everywhere. It's all about noticing a kind of family resemblance in the shapes all around us. So, first things first, we gotta nail down the difference between congruent and similar. Think of it like this. Congruent figures, they're identical twins. Exactly the same shape, exactly the same size. But similar figures, they're more like a family photo. You know, everyone's got the same basic shape, but they're all different sizes. And what's really cool is that some shapes are just born similar. Like any circle you draw is going to be similar to every other circle in the universe. Same goes for all squares and for all equilateral triangles. Their basic recipe is locked in, so similarity is always a given. Okay, but what about more complicated shapes? You know, the kind we need to solve our big measurement puzzle. Well, for those, we can't just kind of squint and say, yeah, they look the same. We need some hard and fast rules to prove it. So for any two shapes to be officially mathematically similar, they have to check two boxes. First, all their matching angles have to be exactly the same. And second, all their matching sides have to be scaled up or down by the exact same amount. You need both. No exceptions. And this right here, this shadow is a perfect example of that second rule in action. See how the light makes a bigger version of the cardboard shape? The angles are all identical, but every single side of the shadow is proportionally larger. It's a perfect scale model. And that same amount we were talking about, that constant ratio, it has a special name, the scale factor. This is the magic number, you guys. It's the key that unlocks the relationship between the small shape and its big brother. If the scale factor is, say, 2, it means the bigger shape is exactly twice as big in every direction. Okay, but checking every single angle and every single side, that sounds like a lot of work, right? Super tedious. But don't worry, because geometry has given us a superhero for this exact problem. The triangle. Yeah, triangles are just special. They're super rigid, which gives them these amazing properties. And these properties lead to some awesome shortcuts, so we don't have to check all 6 parts every single time to prove they're similar. First up, and this is the one you'll see the most, is angle-angle, or AA. See, all 3 angles in a triangle have to add up to 180 degrees. So if you know just 2 angles match up between 2 triangles, well, the third one has no choice but to match 2. And that's it. That's all you need. 2 angles, and you're golden. And check this out. Here's why it's so powerful. As soon as you lock in those 2 angles, the whole shape of the triangle is basically set in stone. The only thing left that can change is how big or small it is, which means the sides have to be proportional. It's automatic. All right, our next shortcut is side, 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 or SSS. This is kind of the flip side of the coin. If you can prove that all 3 sides of one triangle are scaled by the exact same number to get the sides of the other triangle, then you know for a fact their angles have to be identical. Basically, when you stretch or shrink all the sides perfectly in sync, you're locking in the shape. You just can't change the angles without messing up those perfect side ratios. And last but not least, we've got side angle side, or SAS. This one is a really neat hybrid. It says if you have one matching angle and the 2 sides that make that angle are proportional, then bam, the triangles are similar. Yeah, think of it like an angle sandwich. You've got that one equal angle squished between 2 sides that have been scaled perfectly. That's all it takes to lock everything else into place. All right, we've got our rules, we've got our triangle shortcuts, we're ready. Let's go back to that impossible measurement problem and see how this all works in the real world. So this classic lamppost problem, it's basically our measuring a mountain problem, just on a smaller scale. We've got a lamppost, we know how tall it is, and we've got a person, we know their height too. And as she walks away, the light creates 2 different triangles. Okay, so we know a few things here. Now look closely at those two triangles. There's the big one made by the lamppost and the little one made by the girl. Now, assuming they're both standing up straight, they both make a 90-degree angle with the ground. Angle number one, check. And look, they both share that exact same angle way out at the tip of the shadow. Angle number two, check. So what does that mean? Angle, angle. We've got similar triangles, for sure. And since we know they're similar, we can set up a ratio. The height of the big triangle over the height of the little one has to equal the base of the big triangle over the base of the little one. You plug in the numbers we know, do a tiny bit of algebra, and boom! The shadow's length is 1.6 meters. We just measured something without actually touching it. So, okay, that's a cool trick. But why does it really matter? Because this isn't just about shadows and lampposts. This principle of similarity is a fundamental tool we use to map our world, to build our cities, to understand the sheer scale of everything around us. Yep, it all boils down to this one simple idea. Same shape, different size. That's it. But from that simple idea, we get blueprints for skyscrapers, we get maps of the entire planet, and we even get a way to measure the distance to the stars. It's literally everywhere. So now you know the secret. Now you have this superpower of seeing similar triangles out in the wild. So my question to you is, what are you gonna measure? The height of that big tree in your yard? The width of a river? The world is full of these puzzles, and now you have the key to solve them.